Hi, I'm done with mathematical formulation of quantum mechanics. From now on we will move with quantum mechanics, that is the physics of quantum mechanics. So today is Stern Gerlach experiment. So let me show what is doing here in Stern Gerlach experiment. It is a oven, okay, and Ag atom is coming from this oven and it is going past this inhomogeneous magnetic field, okay, and then it is coming to the screen. Now inhomogeneous magnetic field, what does it mean? Inhomogeneous magnetic field is that magnetic field everywhere is not same, like the magnetic field here and here is not same. Homogeneous magnetic field means that magnetic field is same everywhere, okay, but inhomogeneous magnetic field is, it varies with place to place. So suppose the magnetic field varies only with the z direction, okay, so we only need the z direction, we are not interested in x and y, okay, and the magnetic field is also directed on z direction, okay, so we are not interested in x and y, okay, so forget about everything. B, magnetic field is directed in z direction and magnetic field is only varying with respect to z, okay. So in classical electrodynamics we know that inhomogeneous magnetic field not only makes a torque in a magnetic dipole moment, but it also makes a force, okay. So we have a, say, mu is a magnetic dipole moment, okay, and we have this inhomogeneous magnetic field. So what does it do? It makes a force, okay. So what is the force? The z component of the force is okay. So this is the definition of Fz. Now mu and b is a dot product. Now I told that b is directed in z axis, so there will be mu z b, and mu z comes out of this differentiation and this is z direction. So okay, so for a fixed inhomogeneous magnetic field, this one is constant. So the force, the z direction of the force is proportional to mu z, okay. So force is proportional to mu z, okay. Now from atomic physics we know that magnetic dipole moment of an atom comes from the orbital angular momentum, okay. We don't know about spin yet, okay, so forget about spin. If you know about spin, forget about it. So it is yet to be discovered, okay. So force is proportional to mu z, that is the z component of magnetic dipole moment, and magnetic dipole moment comes from orbital magnetic dipole momentum, okay. So the formula is that mu, the magnetic dipole moment, is proportional to L. This is L is the angular momentum, okay, just angular momentum, but we will call this later as orbital angular momentum. Just it is angular momentum, and mu is proportional to L. So mu z is proportional to Lz, okay. So force is proportional to Lz. Now what is Lz? From atomic physics we know that Lz, from Bohr's theory or Bohr's postulate, we know that Lz is not continuous, okay. Lz has some discrete values. So if L is the azimuthal quantum number, okay, I hope you know about this because I have assumed that you have read atomic physics. So small h is azimuthal quantum number. So Lz will be from minus LH to plus LH with integers value. Integers values means minus L plus 1 minus L plus 2 dot 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 L minus 2 L minus 1 L. Okay, so the discrete values of Lz has 2L plus 1 values. Okay, so Lz has 2L plus 1 discrete values. So the force should also have 2L plus 1 values, right? So the force when Ag has gone past this inhomogeneous magnetic field, we will see the force applied on the Ag, and the force will have 2L plus 1 discrete values. Okay, now if L is 0, the force should have L equals 0 means 1, only one value force, it has only one discrete value. If L is 1, 2L, 2 into 1 plus 1, so 3, L is 2, so 5, all odd numbers. Okay, so what we expect to see here is that either we get one spot for L equals to 0, or we get 3 spot for L equals to 3, or we get 5 at 1, 2, 3. Okay, so either 1 or 3 or 5 or 7, all odd numbers. So we are expecting odd spots here. Now let's come to specifically Ag. What is the electronic configuration of Ag? Well, Ag has 47 electrons, so 46 plus 1. Okay, and all 46 electrons have total L or angular momentum equals to 0. Okay, so the net angular momentum of Ag only is for this electron. Okay, and this electron is 5s1. So the angular momentum Ag is for the angular momentum of this one. What is the small l azimuthal number, quantum number for this Fs1? It is L equals to 0. So for Ag, the force component should have 2 into 0 plus 1 equals to 1 for Ag, because L equals to 0. So we should have only one spot here. Okay, but in reality, in experiments, we see that we don't get one spot. We get deviation and we get 2 spots. This is forced. Okay, we should have got one, but we have not got one. At least we should have got odd numbers. Right? 12 plus 1 is a odd number as L is integers only. But here we have 2 spots. So somehow we have missed something. It is that the mistake is that we told that the source of magnetic moment is only orbital angular momentum, but in reality there is another factor. There is another source for magnetic dipole moment. What is that source? For that source, we get these 2 spots. Let's say we have another kind of angular momentum apart from the orbital angular momentum. Apart from L, suppose we have another kind of angular momentum. Let's denote it as S. We don't know what S means. So S is another angular momentum, and this angular momentum gives rise to these two things, these two spots. Now L gives rise to 12 plus 1 spots. Now we have no reason to believe that the formula for S would be different from 12 plus 1. We expect it from that. Here it should be from this. It is same as this formula, but here A small l is for this one. So we should have another kind of azimuthal number, right? Not azimuthal number, another kind of quantum number. Let's denote it as small s, 2s plus 1. Okay. And 2s plus 1 for Ag is only 2. Now Ag means what? When I am saying it is Ag, but effectively it is just a 1 electron, because the 46 electron has no effect on any kind of experiment here. Okay, so it is basically 1 electron. So for 1 electron, this 1 electron do not have this, but has this only, because for this we should have got only 1 spot, but we don't have we don't see any undeviated spot. We see deviated and 2 spots. Okay, so for 1 electron, for I S1, it is 2s plus 1, and 2s plus 1 is 2. So this is 2. Now what is the value of S then? Half. Okay, L is integer and small s is half, and we call this S as spin. Okay, because this is orbital angular momentum and this is spin angular momentum. As L has a kind of algebra, like the value of L square is L plus 1 into, L is root over L plus L into L plus 1 into H cut. For this S, same formula. Okay, we have no reason to believe these two follow different formulas, because these two produce same kind of effects. So this L is also kind of angular momentum, capital S, which is spin here, is also kind of angular momentum. So these two follow same algebra. Just as Lz is ml h cut, Lz is also ms h cut. Where ml have values minus L to capital L, small l. Here ms has values from minus small s to capital small s. Okay, so we have introduced spin. Okay, and from the spin we get 2 deviation. Now as ms is minus s to s, here s is half, so ms has values only minus half and half. So one is for half, another is minus half. Okay, so when I have an electron and I make this electron go past inhomogeneous magnetic field directed in any direction, say z, okay, this gives me 2 deviated spot here, and one is for ms is equal to plus half state and one is for minus half state. We call this state. Just as polarization, we have circular state, we have linear states. Here ms is equal to half is a state, ms is equal to minus half is a state. Okay. So spin half has plus half state and minus half state. Okay, this is for z axis. Okay, so if this is S, the spin Sz has plus half or minus half. Let h cut be 1. Okay, but changing the unit, h cut is 1 in this unit. So Sz is plus half and minus half. Okay, so now there is nothing sacred about this z direction. We can have x direction also. Like if instead z is x, then Sx should also have plus half minus half, or even y. Sy can have value minus half and plus half. The main thing is that whenever I try to find the component of S in any fixed direction, either a z or a x or y or any n cap direction, we should have only two values, plus half or minus half. Okay, so this is the case, and plus half is a state and minus half is a state, and these two are orthogonal states because these two are two different kind of states. Okay, so we can prove this experimentally that these two are different kind of states. Okay, so let's simplify things. Electron going, I mean this may not be electron, this is just spin half. Okay, this is spin half, and there is Stern Gerlach experiment going on directed in z axis, so we will denote Stern Gerlach as z, and this will deviate to Sz plus and Sz minus. Sz plus is that plus half, Sz minus is minus half. Okay, now I told that these two are orthogonal. How? If I do another Stern Gerlach experiment on this along z direction, suppose we have blocked Sz minus. Only thing I have is Sz plus, and I am doing Stern Gerlach experiment along z axis on this state. We will never get this one. We will always get Sz plus. Now ask me why. I told that reason that whenever what is going on here? I have a state S is equal to half. Now I am doing an experiment. I am doing a measurement. Whenever I do a measurement, the state collapses. It collapses to different states. This is actually kind of superposition of these two states because we get two different results. So this state is actually superposition of these two states. C1 up, suppose positive means up, plus C2 down. Up and down are states which denotes Sz plus or denotes Sz minus, and this is K. A state is denoted by K. So C1 up, this is directed upward, so this is up, plus C2 down. So Sz does what? Sgz is a measurement. It makes this state collapses to this state for this one and for this state. Some electron, okay, we don't have only one electron here, we have many electrons. Suppose we have n electrons. For n1 electrons, this state collapses to positive up, and for other electrons this state collapses to down. That is why we get n number of electrons as Z plus and n2 number of down as Z minus. And I am blocking this one. Okay, so the only state is this. So as the state has been already collapsed, if we make another same measurement, it will remain in the state. The result will not change. So this is expected. The whole thing is expected. So up and down are orthogonal states. Okay. If they are not orthogonal, we should have got some Sz minus here. But we don't have any Sz plus. In experimental fact, we don't have Sz minus here. We only have Sz plus. So Sz plus is only consists of Sz plus. Okay. So mathematically I am saying that the up state and the down state are orthogonal, means the scalar product between these two is 0. Okay, this is all expected, and this is the mathematical formula for orthogonality between two states. Okay, now suppose spin half SGZ, so we get two deviated particles. One is SZ plus and another is SZ minus, and we block this one. We have blocked SZ minus. Okay. Now I am doing SZX. For this Stern Gerlach experiment, I have pointed my magnetic field along x-axis. Okay. So if on this state we have done this experiment, we should have get what? Sx plus or Sx minus. We told that for any direction, if I want to measurement of, if you want to make a measurement on this state, it will give you a plus or minus. As this is x direction, it will give me Sx plus, Sx minus. So I am not doing this experiment on this state. Okay, I am doing this experiment on Sz plus. So what should I have here? The result is that Sx plus and Sx minus. So this is same as this one. If I try to make measurement on x-axis, I get both Sx plus and Sx minus. Similarly, if I want to try to make a measurement along x-axis to know the x component of spin of the state which is already in this Sz plus, I get Sx plus and Sx minus. So does it mean that Sz plus is equal to half? Here will be 1 by root 2 because of normalization. Okay, so 1 by root 2 of this should this be the formula, because when I do experiment on this one, we get this and this. Okay. So this is Z plus. Is it supercomposition of Sx plus and Sx minus? We'll see that later. Now let's move on to another experiment. This is number 1 question. Okay, let's move on to another kind of experiment. Same thing, x is half SGZ SZ plus Sz minus. I have blocked Sz minus. I blocked Sz minus. I am doing Sgx. From the previous experiment, we know that this will give me to Sgx plus, xx plus and x minus. Okay, this is known as just previous experiment. And now we block this sx minus. Okay. Now I am doing another experiment on this Sg along z direction. I am trying to find on this sx plus which has come from this sz plus. This is sx plus is a part of this one because sz plus gives rise to two sx plus and sx minus. So from this sx plus I am trying to find that what will be the component along z direction. I have what will be the possibilities here. Whenever the spin at least have only two components, either plus or either minus. So as this is z direction, the outcome should be sz plus or sz minus. Okay, the outcome will be this or both or neither. So this should be the result. Okay. Now I told you previously I have blocked Sz minus. So the electrons that are going on these state Sgx, Sgz do not have this Sz minus. Now should this lead me to say that this should be only Sz plus because Sz minus already removed here. So our classical intuition tells us that the result should be only Sz plus because I have omitted this one. In these electrons we do not have this component, right? But this experiment tells us that this has Sz minus 2. Where does the Sz minus comes from? I have already omitted Sz minus. So in this electron there is only Sz plus component. Now again I am getting Sz minus. Where does the Sz minus comes from? This experiment is purely quantum mechanical. These experiments have the mystery of quantum mechanics. Okay, the main mystery of quantum mechanics lies on this experiment. Okay, now let me give me a hint here why this is happening. Now suppose I have only Sz positive here. Suppose we do not have Sz minus. Now it will mean that I have Sh plus and I have Sz plus in these electrons. The electron, if I do a measurement on Sgx, it will give me Sx plus because this is only Sx plus, right? This is only Sx plus. It gives me Sx plus, and when I do experiment along z direction, if I have only Sz plus, so then simultaneously I have Ss plus and Sz plus. Okay, so let me tell this again. Suppose Sz minus is not present here. Okay, we have only Sz plus according to a classical intuition. So it means that in this electron, obviously the x component of S is Sx plus in this electrons because we have just obtained this state. So if I do again Sgx, we get this one. Okay, so this electron already has Sx plus. So on top of this, if I have Sz plus. Then in this electron we can tell simultaneously that the X and the Z component of electron has plus factor. Okay, so if this is the case, so we can say simultaneously that Sx is plus and Lz is plus. If this is the case, but here we are getting this one. So it means that this experiment, the quantum mechanics or nature, somehow prohibits this. Because if I get Lz positive, it means this. That is why I am not getting Lz plus, I am getting both. I am getting both. I am getting Lz plus and minus, both. So we cannot simultaneously say that Sx is positive and Lz is positive or negative. Whenever I fix Sx to be positive, Lz cannot be fixed to plus. Lz can be plus half, Lz can be minus half. So nature prohibits this. Nature prohibits to let us know, or nature prohibits, or nature it does not exist. I must say that the component of S along x-axis and component of S along z-axis do not exist simultaneously. This experiment shows me this one. Okay, I hope you get this. The component of S, the spin, okay, the component of spin do not have two components simultaneously. It may have this component Sx. If this is fixed, this one is plus or minus, just like this one. Think about this. I have fixed a Z component of S to be plus half. As soon as I fixed Lz to be positive, the X component will have plus and minus. Similarly, when I fixed this, the Z component of S will be plus and negative. So the component of S along two different directions, two orthogonal different directions like S and Z cannot exist simultaneously. So this is kind of a mystery in quantum mechanics. This will lead me to a principle. And this principle is widely known. You know the principle. I'm not going to name it right now. So that's it. The Stern Gerlach experiment is very much important in quantum mechanics. So it tells the philosophy of quantum mechanics, just like this one. A vector can have two components simultaneously, just like this one. A vector which is suppose V has, if it is X and Z, it has X component and it has this component. Simultaneous, we can say this, but in quantum mechanics, we cannot say simultaneously the X component is half or this is half or it's half or half. We cannot simultaneously say the component of X as simultaneous component of Z, component of Z of this spin vector S. Okay, so this is quantum mechanics. Why this is happening? This is the principle. Why this is happening, I cannot tell. I can only tell how this is happening. Okay, so that's it for today. Thank you.